All right, so today we're going to talk about section 8.1, which introduces the concept of identities in terms of trigonometric functions. And you'll recall from the last chapter that we talked about sine, cosine, and tangent being related to the x and y coordinates of a point on the unit circle. All right, the next section talks about the Pythagorean identities. So the reason why this is called the Pythagorean identity is if you consider a right triangle where the one leg is labeled as x and the other leg is labeled as y, to get the measure of the third side, you could use the Pythagorean theorem. So instead of saying a squared plus b squared equals c squared, you would say that x squared plus y squared is equal to 1 squared, because on the unit circle, that radius or the hypotenuse is equal to 1. And since we know that the x coordinate of a point on the unit circle is equivalent to cosine of t, we could square that, and we use the notation cosine squared of t. So you put the squared in between the cosine and the t as opposed to on the outside. That way you don't have to deal with any parentheses. And we'll do the same thing for the y coordinate, that is sine squared of t, which we're going to write that instead of saying sine of t squared, and we know that 1 squared is equal to 1. So that is where this identity comes from. An identity is an equation, or basically a formula, that we know holds true for all values of t, no matter if they're positive or negative. So if we were to take this identity that we already know is true, sine squared plus cosine squared equals 1, and divide it all by sine squared of t, as you see in this equation, we could reduce, and we know that sine squared over sine squared would give us 1. Cosine over sine, which is cotangent, but since it's squared, it would be cotangent squared. And then 1 over sine we know is cosecant, so since it's 1 over sine squared, this would be cosecant squared. All right, so the secondary Pythagorean identity is 1 plus cotangent squared of t is equal to cosecant squared of t. If instead of dividing by sine squared of t, we divide by cosine squared of t, we could reduce each of these three fractions to get this third Pythagorean identity. So we know that sine over cosine is equal to tangent. So if we have sine squared of t over cosine squared of t, that we know is tangent squared of t. And anything over itself is going to be equal to 1. And then 1 over cosine is secant, so if it's 1 over cosine squared, then it's secant squared of t. All right, so our next set of identities are the opposite angle identities, and we're going to use this diagram to prove that these are in fact true. We know that this point on the unit circle has an ordered pair of root 2 over 2, comma, root 2 over 2. So these opposite angle identities, if you notice, the negative and positive version of that angle is still going to be the same thing. So cosine of an angle and cosine of a negative version of that same angle is still going to be the same. And if you look at this diagram, the cosine would be the x coordinate. So for this particular angle of pi over 4 compared to negative pi over 4, both of the x coordinates are root 2 over 2. When you look at the sine identity, we have sine of a negative version of the angle. So if we look at the negative pi over 4 as compared to sine of positive pi over 4, what changes is the y coordinate is now the opposite. So the y coordinate for the positive angle was positive root 2 over 2. And when we flipped it over into the fourth quadrant, the y coordinate of the negative version of the angle was negative root 2 over 2. Now, your original t angle doesn't have to necessarily be positive or in the first quadrant. It could be in any quadrant. It could be a negative angle to start with. But if we were to take the opposite of it, the y coordinate will flip. If we were to look at tangent of pi over 4, we know that that's equivalent to y over x, and that would be root 2 over 2 over root 2 over 2, which we know is equal to 1. Then if we were to calculate tangent of negative pi over 4, that would give us negative root 2 over 2 over root 2 over 2, which would give us negative 1. So notice that the tangents of angles that are opposites of one another are also opposite of one another. So the angle is opposite and the tangent is opposite. So we would say that the ratio of y over x is the opposite. So you don't have to necessarily memorize these identities as long as you can calculate them out. If you use an example angle for yourself, draw it out, and then find the opposite of that angle, you should be able to figure out what these three identities are. For the periodicity of sine and cosine formulas, we do know that if we rotate around the unit circle k amount of times, that adds 2 pi to the angle, but that does not change the sine or cosine of that particular angle. And so that's where those formulas come from. So we're going to use the concept of coterminal angles in order to figure out what is the cosine of 9 pi over 4. So we know that cosine of 9 pi over 4 would be equivalent to pi over 4, but going around the circle one additional time. So therefore, whatever we would normally get for cosine of pi over 4 would be our answer to cosine of 9 pi over 4. And if you recall, the x-coordinate of a pi over 4 angle on the unit circle would give us root 2 over 2. On part B, we're going to use the opposite angle identity, and we know that cosine of a negative angle would be equivalent to cosine of a positive angle, since the x-coordinate doesn't change, and therefore the answer would be exactly the same, root 2 over 2. For sine of 9 pi over 4, we're going to think about coterminal angles. So sine of pi over 4 would be equivalent to going around one additional time around the circle. And so sine of 9 pi over 4 would equal sine of 1 pi over 4. And now we'd be thinking of what is the y-coordinate at that point on the unit circle, and that would be root 2 over 2. So notice that the x and y coordinate are the same because this is a 45, 45, 90 triangle, which is isosceles. All right, for part D, we're going to look at the opposite angle identity, and we know that sine of a negative angle is equal to the opposite of sine of whatever positive value of that angle. So we would look at what we got in part C, and we would take the opposite of that, so it would be negative root 2 over 2. Number 2, it wants us to check that both sides of the identity are equal if we use the angle to be 3 pi over 4. So if I were to do tangent of 3 pi over 4 squared plus 1, and we're going to see if that is equivalent to secant of 3 pi over 4 squared. All right, so now we need to figure out, well, what is tangent of 3 pi over 4? If it helps, you can draw out the angle in the coordinate plane. So 3 pi over 4 would be in the second quadrant. It would create a 45-degree angle. So this point at the end of the unit circle would be negative root 2 over 2, comma, positive root 2 over 2. All right, so that would be my x and y, or my cosine and sine. And we know that tangent is y over x. So we would get root 2 over 2 over negative root 2 over 2. And that we know reduces to negative 1. But we have to square that. We would find the reciprocal of the x-coordinate, which is 2 over negative root 2. But we have to square that. So if we square that, we would get 4 over positive 2. Right, and then let's just verify that both sides of the equation are equal. So we have negative 1 squared. That's 1. 1 plus 1 is 2. And 4 over 2 is 2. So indeed, both sides of the identity are equal. If we look at part B, now they want us to use an angle of negative 2 pi over 3 in this equation. I'm going to do the same thing. If it helps you to draw out the angle, we have negative 2 pi over 3, which would go 2/3 of the way to the x-axis on the left side. And so that would leave us with a 60-degree angle left over. And so we know that this x-coordinate would be negative 1/2, and the y-coordinate would be negative root 3 over 2. All right, and that's our x and y, or our cosine and sine. So for tangent, we know that's y over x, so it's negative root 3 over 2 over negative 1/2. And that reduces to root 3 because our 2's in the denominator would cancel out, and the negative signs would also cancel out. We do have to square that, so square root of 3 squared is just positive 3. Then we can bring down the plus 1. And then secant is the reciprocal of cosine, so we're going to flip over our x coordinate, but we have to square that, so that would give us 4 over 1, which is 4, and indeed 3 plus 1 does equal 4. For number 3, we're going to show that this identity is not actually true, so it is not an identity, and we're going to use the angle pi over 6 to prove that. So if you draw that out, pi over 6 is in the first quadrant, and that creates a 30-degree angle, so we know that the x-coordinate is root 3 over 2, and the y-coordinate is 1/2. We're going to substitute in, so we have cosine of 2 times pi over 6 equals 2 times cosine of pi over 6. On the left side, we need to multiply 2 times pi over 6, which gives us pi over 3. So we're going to need to draw another angle on our coordinate plane there. But 2 times cosine of pi over 6, we have our cosine is our x-coordinate, so that would be 2 times root 3 over 2, which would give us just root 3. All right, so now if I draw another part of my diagram to include a pi over 3 angle, that's a 60-degree angle, so those coordinates are 1/2, comma, root 3 over 2. And so cosine is our x-coordinate, and 1/2 is definitely not equal to root 3. So we have proven that this is not an identity. In number 4, they want us to substitute in 3 sine of theta in for x. So I'm going to rewrite this as square root of 9 minus 3 sine theta, and we're going to square that. But now they only want us to use angles that are in the first quadrant and prove that it becomes 3 cosine of theta. So think about what happens in the first quadrant between 0 and pi over 2. Every ordered pair in the first quadrant ends up being positive for the x-coordinate and positive for the y-coordinate. So let's simplify algebraically a little bit. We have 9 minus, and then when we square it, we have 3 squared, which is 9, and sine squared. So since we have a binomial, if we could try to factor, I see that there's a GCF, and I could factor out a 9, and I have 9 times the quantity 1 minus sine squared of theta. Now, 1 minus sine squared theta looks familiar because we had an identity earlier that looked like sine squared t plus cosine squared t equals 1. And if we were to solve for cosine squared t, we would get 1 minus sine squared t. And so we could substitute the 1 minus sine squared t. We know that theta and t are the same thing because it's just any angle. So this binomial would become cosine squared of theta times 9. And we still need to take the square root of that. So when you take the square root, it's just positive anyway, and it will give me 3 cosine of theta. Moving on to the last 2 problems. Problem number 5 involves the opposite angle identities. So if we do sine t equaling 2/3, we know that sine of negative t is equivalent to negative sine of positive t. And if sine of t is equal to 2/3, then we know that this quantity is equal to negative 2/3. Same thing for the second one. We know that sine of negative theta is equal to negative sine of theta. So if we know what sine of theta is equal to, it's negative 1/4. We have negative 1/4, which becomes positive 1/4. For cosines, when we do the opposite angle identity, cosine of negative alpha is going to be equal to cosine of positive alpha, and cosine of negative beta is going to be equal to cosine of positive beta. So whatever answer we had for cosine of alpha earlier, we would just replace, and this would give us 1/5. And for the next one, cosine of beta was negative 1/5, and so that stays the same here. Number 6 involves the periodicity of sine and cosine formulas, which is essentially going around to coterminal angles, you rotate around 2 pi or negative 2 pi, depending on which direction you're going, as many times as you need to. So by going once around the unit circle, this expression is still the same as sine of pi over 4, and that's a 45, 45, 90 right triangle, so that gives us a y-coordinate of root 2 over 2. For cosine of 5 pi over 6 plus 6 pi, this is just going around 3 times. And so you would just end up in the same exact location as the original angle of 5 pi over 6. If you don't remember where 5 pi over 6 is, that creates a small angle here, so that's a 30-degree angle. And so this ordered pair would be negative root 3 over 2, comma 1/2. And since we're looking for cosine, that would be our x-coordinate. So negative root 3 over 2. And for the last two problems, now you have to think about, oh, how do you get sine of 7 pi over 2? Could I add 2 pi to some angle and get 7 pi over 2? Well, yes, if I started with 3 pi over 2. If it helps to write it out as 3 pi over 2 plus 4 pi over 2. Now you could see that that gives you 7 pi over 2. So this would be equal to sine of 3 pi over 2. And 3 pi over 2 is like a 270-degree angle going around past 3 quadrants. And so that has an ordered pair of 0, comma, negative 1. And so we are looking for the y-coordinate, which would be negative 1. For cosine of 19 pi over 3, we need to figure out cosine of what angle plus some amount of revolutions around the circle would give us 19 pi over 3. So if I add on 18 pi over 3, that would be 6 pi over 3. So I know I would have to go around 3 times. If you have trouble thinking of this, you can go backwards. So 19 pi over 3, subtract 2 pi, right, which would be 6 pi over 3. That would give me 13 pi over 3. And then keep subtracting off until you get to something that's within the first revolution around the unit circle. So once I have 7 pi over 3 and I subtract off 6 pi over 3, now I know I get down to 1 pi over 3. So that's how I know what my original angle would be before I rotate around the unit circle 3 times. So now I'm just thinking of, well, what would cosine of pi over 3 equal? And that creates a 60-degree angle. So when it has a 60-degree angle, then that x-coordinate would be 1/2. If you want to verify that number 6 is correct, you could use your calculator and you could go to your mode and double check that you're in radian mode. And then you could quit out of there and go to sine of pi over 4, which is the square root of 2 over 2. Our original problem was actually sine of pi over 4 plus 2 pi. And if you're not sure that that is the square root of 2 over 2, you could type that in and just double check that those decimals are equivalent. Or you could memorize what is the square root of 2 over 2. Cosine of 19 pi over 3, you could do the same thing. And you should get 1/2, which we know is 0.5. All right, if you have any questions on this topic, please ask your teacher. Have a nice day.